Welcome to the special talk, Time Domain Analysis of Open Cavities. My name is Cheng Zhang存续in Chinese. This special talk is designed for microwave physics and applications, and the lecture notes and computational exercise for graduate students, graduate course. The PowerPoint file is based on Professor Collin 朱国瑞院士 lecture notes. His lecture note about time domain analysis of open cavities. What is open cavity? Why we want to discuss open cavity? Here is the outline. First, I will give you a brief introduction of open cavity, and then I will show you the formulation, numerical algorithm, and then I will provide Fortran exercise or other softwares. Then we will discuss, and we will have some appendix, including spectral domain analysis of open cavity. We have time domain, we have spectral domain. Okay, here is the outline. Okay, what is open cavity? Closed cavity, easy to understand, well-defined boundary. However, open cavity like this one, left-hand side is open, right-hand side is also open, but in this region, normally it's cut off. Wave cannot propagate. So looks like open, but effectively like closed. So that just looks like semi-open waveguide. But here we have discontinuity. So we will have some reflection. So it's partially closed or partially open. This kind of structure is good for generation of high power radiation, such as interaction structure of gyrotron, electron spectrometer. Okay, captions shown here. Illustrative model of an open cavity section less than Z2 is a cut-off waveguide for electron beam. So in this section is cut off. Electron beam can enter, and electron beam entrance. And the section between Z2 and Z3 from here, uniform section, is the main body of the cavity. The section from 3 to 4 is slightly tapered to provide partial reflection. So wave will partially reflected back to the cavity and partially transmitted to the output section, such as greater than Z4. Open cavities are employed in gyrotrons for the generation and extraction of high power millimeter wave or terahertz wave radiation interaction structure. And resonance characteristic depend on the structure. This is a low Q resonance circuit due to the open end structure here. And the materials are self-contained and self-explanatory. Okay, a complementary spectral domain model can be found in appendix. So we will talk about a spectral domain model later on, frequency domain. Okay, now let's consider the formulation. Consider a typical open cavity formed of multiple sections of uniform, and linearly tapered structure, tapered. Find the resonance frequency omega r and the quality factor, Q factor. So for this system, the most important parameters are resonance frequency and Q factor. And we are going to make 3 assumptions. The waveguide radius changes slowly, and there is no mode conversion. Okay, it might occur to you, in here, it's not slowly, it changed drastically. However, here, okay, acceptable, slowly, but here is definitely not. But don't worry, later on, I will show you, even though it's discontinuous here, the result is still acceptable. But with single mode operation, the calculation can be simplified. A resonance mode is initially present in the cavity. Okay, all fields vary with time as exponential negative I omega t. So initially present in the cavity. So looks like just consider a black body of very, very broadband. So since there is a resonance condition here, so therefore, initially there is a mode here, although the value is very small, okay? The end sections are uniform, and left section, right section are uniform to ensure the correctness of the calculation. Yeah, uniform, much easier to deal with for this section. And I will show you these three assumptions will have these three assumptions will have exceptions. Okay, so resonance frequency omega comes from real power as well as imaginary power, where omega I will be less than 0. Therefore, the energy will resonate as well as exponential decay. Okay, from this viewpoint, time domain, so they will change with time. Okay, so let's just consider TE mode, the time dependence of field components, say BZ. For TE mode is BZ. Once we have BZ, we can calculate EX, EY, BX, BY, ES, EY, EZ. So BZ is the most important components for TE mode. And we just assume BZ is proportional to exponential negative I omega t, real power, imaginary power. A real power, imaginary power. So field energy is proportional to BZ squared, absolute value squared. So it will be exponential decay because omega I will be negative, less than 0. The power loss, the field energy stored as it changes with time change rate, and equals to omega I times the field energy. So the quality factor of the cavity will be the omega R times the field energy divided by power loss. So happen to be omega R real power resonance frequency divided by 2 times the absolute value of omega I. Okay, that means we can obtain a time domain model. All we need to do is calculate omega, complex omega, or resonance frequency together with quality factor of the cavity. Okay, so now let's focus on single mode, simplest case, TEMN mode. For a circular waveguide or cylindrical waveguide with slowly varying radius, so radius just change slowly. The wave equation for TE mode is expressed in a cylindrical coordinate system as here. F of z is to be determined, can be considered as amplitude, Bessel function, and argument is function of kzmn z. Kmn function of z depends on position times the radius of the circular waveguide times exponential I m theta minus I omega t. Now, we are going to apply the boundary conditions on the side wall. So with the boundary condition, you can use a boundary condition to determine on the side wall, on the metal wall. On the side wall, the simplest one is you have multiple choice. Normal component of BZ, that will be BR, should be 0. Or tangential component of electric field, that will be EZ, will be 0. Okay, on the side wall. So you can use either one. Either one is okay with us. So with this one, we got a boundary condition on the side wall. This gives us on the side wall when R equals R omega, some typo here. So we can determine cutoff frequency. We can determine KMN as function of waveguide radius. Okay, here it should be lowercase, where SMN is the nth root of Bessel function prime. Okay, first derivative of the Bessel function of order m. Substituting to the wave equation, we obtain these conditions. S component, transverse component has been cancelled, and is function of z, second order ordinary differential equations. And Kz, remember we have two sections. One section, if Kz can be determined from this equation. If this is above cutoff, then Kz will be real, propagating wave, forward propagating or backward propagating. However, Kz, if this one is less than 0, that's for below cutoff, and what will happen? This one will be complex. Will be complex below cutoff, exponential growing or exponential decay. Okay, below cutoff, that will be kappa. So two conditions, depends on the geometry. Okay, so f of z above cutoff should be this form. Below cutoff should be this form. Exponential growing, exponential decay. Forward propagating wave, backward propagating wave. Where omega CMN is the chi mn times c. C is the speed of light divided by RW. RW is the waveguide wall radius. The complex function of f of z takes the general form. F of z should be this one. Depends on z as well as here. This is the as a phasor, consists of amplitude and phase information. The dependence of f of z and phi of z on z indicate the nature of the wave. Let's simplify this one. For a pure traveling wave, one A equals 0, B non-zero, or B equals 0, A non-zero, then f of z will be independent of z. And phase part will move to here, to phase. But phi is a linear function of z, kz times z, or negative kz times z. So for a traveling wave, A, B, forward wave, backward wave. For a pure standing wave, A equals plus O minus B. And f of z is sinusoidal function. Sine or cosine is a standing wave. Wave cannot propagate for this condition. For a decaying waves at both ends, exponential decaying wave, phi of z is independent of z. Phi of z, because we have real component only. Real and real. So what's next? We want to determine the coefficient. How to determine the coefficient? Use the boundary condition to determine f of z and phi of z. We are going to determine this phasor, f of z, amplitude, and phase, okay? We already used the boundary condition on the side wall, but remember we have two upstream and downstream. I mean the left-hand side as well as right-hand side boundary condition. So what kind of boundary condition should be employed? We use outgoing wave boundary conditions. So initially we have wave in the middle, and wave will propagate or decay. Okay. So initially there is a field profile satisfying all the boundary conditions and then decaying with time. The field will decay with time. At both ends, we have just propagating wave. At the left-hand side, z equals z1. Wave cannot propagate. No incident wave. So A should be 0. And D, exponential decaying wave. This part, A and D should be 0. So at the left-hand side, A and D should be 0 if above cutoff, below cutoff. And on the other hand, if G5, C and B should be 0. Above cutoff, we use B. No coming from, no incident, no incoming wave. Okay, at G5, right-hand side. And C, if above cutoff, below cutoff, C should be 0. Sorry. Above cutoff, C should be 0. And then, so it should be, depends on above cutoff or below cutoff of the resonance frequency. So we can take this part, the first derivative of f of z at point z1, then it should be here. Just take this part, this condition. And if below cutoff here, actually we just use this one. Yeah, this one. Oh, sorry. And on the other hand, right-hand side, G5, and we use this one. So we use this one for G1 and this one for G5. Okay, now let me show you the numerical procedure step by step. With a proper guess of the value of omega r and quality factor. Initially, we make a proper guess. What is a proper guess? A proper guess then means you can guess widely, doesn't matter. And then f is given at z equals g1. Therefore, f prime is set accordingly, according to this one. Okay, once f of z1 is determined, f prime of z1 is also determined. Okay, let's continue. We guess omega r and q, the complex resonance frequency, and f is given from z according to the equation I just shown. And integrate from Z1 to Z5 based on the equation I just shown. So using the Runge-Kutta method. And then we will check the boundary condition at Z5 using the Muller's method and to guess the next root of omega R and Q. And then do the iterative integration, each time with an improved guess for omega, and will eventually converge to a correct solution for omega. And f of z will satisfy all the boundary condition. Boundary condition, left-hand side at z1 is given. And then with this one, f prime is obtained, and then perform the Runge-Kutta integration for this equation, for this equation, Runge-Kutta equation from the left-hand side to the right-hand side, and then change the boundary condition and use the Muller's method to determine the next possible root, okay? And perform the iterative integration, we eventually can obtain the correct solution. Okay, so what is the boundary condition at right-hand side? At left-hand side, boundary condition at Z1 is given by researcher, and a small value doesn't matter. The absolute value doesn't matter. It's relative value. However, the boundary condition at Z5 needs to be checked. Okay, check the correctness. It's a complex boundary condition, CBC. So we have a subroutine to help us check this one. At the right-hand side, actually, we have two equations, above cutoff, below cutoff. For the current structure, it's above the cutoff. So we use this one. Okay? And we can move to the left. So we use D of W equals F prime at Z5 minus IKZ of Z5 times F of Z5. We use this one. Okay. Standard root finding algorithms such as Muller method can readily used. There are a series of discrete solutions for omega corresponding to different actual modes, assuming that the transverse mode number m and n are given. So we have TE, M, N mode, but they also correspond to different actual modes, transverse mode as well as actual mode. Each transverse mode, each TEMN mode has many actual mode. L equal 0, L equal 1, L equal 2. Okay, various. Or L equal 1, L equal 2, L equals 3. Here are some comments. It's clear that the solution for omega should be independent of the position Z1 and Z5, because Z1 and Z5 are uniform section. So contribute nothing. We just focus on the main cavity. As long as they are in uniform end section. So the length of G1 to Z2, G4 to Z5 doesn't matter. Validity of the evanescent wave boundary condition requires that the end waveguide radius R1 or R2 be smaller than the cavity radius. Okay. It should also be noted that the assumption of slowly varying cross-section is violated at z equals g2, as we mentioned before. This is justifiable only if the left end waveguide is cut off to the cavity most. So not good, but acceptable. Okay. In this case, total reflection at the left end occurs as a more exact model would predict. Okay. This statement is a little bit complicated to understand, but just imagine left-hand side is a cutoff section and lesson wave, and it's uniform. So even though it's not slowly varying cross-section, it's still acceptable. Not much difference. But if we want to consider this effect, we will introduce a new techniques called model analysis. It will excite more than one modes. Okay, model analysis later on. Okay, here is the numerical algorithm. How to integrate a differential equation such as this one. And left-hand side is given. Right-hand side will be integrated based on this equation. So this is a second order ordinary differential equation. We are going to use the Runge-Kutta method to integrate from the left to the right. The second order equation shown above here can be decomposed into the form of coupled real differential equation of the first order. So we decompose a second order differential equation into two coupled differential equation of the first order. And just write f consists of real part as well as imaginary part. So f prime will have real part as well as imaginary part. Kz, okay, also have real part, imaginary part. Kz squared also has real part, imaginary part. Okay, substituting this variable into here, we got two parts. For real or for f df over dz, f with respect to z, differentiate with respect to z, we got this one. And for another one, we got this one. This equation is a complex equation. Complex equation decomposed can be rewritten into a coupled equation. Real part, imaginary part. Much easier to deal with. Okay? And more information. A numerical algorithm. Initially, we have initial boundary condition at Z1. The boundary condition at Z1 can be written as a given. F of Z, arbitrary real constant. Fi, imaginary part, real part, imaginary part, arbitrary real constant. So at the left-hand side, boundary condition, it can be written in this form for this case. Okay, and prime, that's for real part, that's for imaginary part. Imaginary part, we use this one. Look at the mouse, the marker here. So we use this one and this one. Okay, more information. Initial at the left-hand side, final at the right-hand side. A guess value for omega can now be integrated from Z1 to Z5. Use Runge-Kutta. And the result resulting function fr at g phi, fi at g phi, fr prime at g phi, fi prime at g phi gives the complex f and f prime. Give us this one. The procedure is to be repeated with an improved guess until the required accuracy is achieved. Until the required accuracy is achieved. Okay. And a fortune exercise will be provided. The program named the Cavity.f consists of a main program, and the following subprograms will be provided. The general purpose of the subprogram: Muller find the complex root of an arbitrary complex function. See Appendix B. So Muller will help us a lot. Runge-Kutta integration allow us to integrate from the left to the right. See Appendix C. S-scale, S-plot, big scale, big plot, not very useful. You can omit here. And the subprogram written for Cavity is recommended to go over for the contents closely. Complex boundary condition. Evaluate the function of d of omega in equation 19 by integrating equation 24 to 27 with initial value given by equations 28 to 31. Differential equation: evaluate the derivative of the four equations. Radius: specify the cavity wall radius as a function of z. Rho: specifying the wall resistivity as a function of z. One more time. So just specify the value. C loss: evaluate the wall loss factor derived in Appendix E. That's very important and useful. So C loss help us a lot. Not too much equation. Now we don't have to worry too much about S scale, small scale, large, big scale. All we need to do is calculate and extract the data and use other software to plot